Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I would like to give more examples related to basis for vector space. So, in this particular example, you are asked to find the basis for the following vector spaces. So, here is an example of vector space. So, clearly, you are dealing with some numbers here represented by a, b, negative b, and a. So it has to be defined in this way. It has 4 dimensions. So you have to think about the possible set of vectors to be considered. And of course, I think the simplest number of vectors that you can consider is having 2 vectors. For example, the first vector here could be something that looks like this. It could be something such as 1, you let a becomes 1, b for example 0, therefore negative b is going to be just negative 0, which is 0, and a is the same value for this one, so here is 1. So this is an example of vector that fits the description defined for vector space here. So the description is such that you have the same value at the first and last component, and for the second and third component here, the value is the same and just different by positive and negative sign. Okay, so this could be an example of vector that you can consider. Okay, and again, like I said just now, it is you require at least more than one, because you need to come up with a linear combination of the vectors, right? So how to combine if there is only one vector? So you need at least 2. Okay, so we're just going to stick with 2 because 2 is at least easier to think of. Okay, so the second vector, think of something simple, a simple number. So it could be a is 0, and then b could be 1, and here is negative 1. So this is a vector that fits the description given here. Now, in order to be a basis, again, we need to check the 2 conditions. The first condition is does this vector, so I'm going to call this b. B is a set of vector 1 and vector 2, which is given by these 2 items here. So in order to be a basis for the vector space, we need to check whether B spans W1, the vector space. Okay, so in order to do that, let's consider combining these 2 vectors together. So here we have C1, the vectors is 1, 0, 0, 1, plus C2, 0, 1, negative 1, 0, and this is should equal to something that can be represented by simple alphabets. So since we already have these alphabets, we can just use it right away. So we can have this equal to A, B, negative b, and a. Therefore, we need to be able to show that we have values for C1 and C2. And in order to do that, we shall consider the augmented matrix. Okay, so the augmented matrix will look like this: 1, 0, 0, 1, 0, 1, negative 1, 0, and here is A, B, negative B, A. Okay. And clearly what we can do next is we can turn this into 0. So therefore R4 plus negative 1 R1 will do just that. So here we go, 0, 1, B, 0, negative 1, negative B. Here is 1 minus 1 is 0. 0 plus 0 is 0. A minus A is 0. Okay, the next part is to turn this into 0. So we have R3 plus 1 R2. And here we have 1, 0A, 0, 1B. For this one here we have 0, 0 plus 0 is 0. Negative 1 plus 1 is 0. Negative b plus b is 0. And here is at the bottom. And we have come to the simplest form of augmented matrix, where you can clearly see that for this part here, we have the value of C2 equals to B, and the value of C1 here equals to A. Therefore, since we have managed to come up with values for C1 and C2, we can then write in this form. So therefore, we can write it in terms of, well, here we have A times with the first factor 0, 0, 1 plus B with vector 0, 1, negative 1, 0, and the result here will be A, B, negative B, A. And because of that, we can say that since the two vectors here can be written as a linear combination, therefore B, which is defined by vector 1 and vector 2 here, spans W1. So here spans W1. Okay, right, now let's move on to showing the second condition, which is we need to demonstrate that B is linearly independent. So is B linearly independent? Okay, so for this one, the starting point would be, this is supposed to be C1 and C2, yeah? Okay, so for B being linearly independent, it means that we are going to consider this process plus 0, 1, negative 1, 0, and this must be equal to vector 0. Okay, so what you can do is, again, you can consider the augmented matrix. So it will be represented as such: 1, 0, 0, 1, and then we have 0, 1, negative 1, 0. Here is 0, 0, 0, 0. So in a similar way as what I have shown just now, what you can do is maybe turn this part into 0. So here is R4 plus negative 1 R1, and you will get the following answer: 0, 1, 0, 0, negative 1, 0. So 1 minus 1 is 0. Oops. 1 minus 1 is 0. 0 minus 0 is 0. 0 minus 0 is 0. Okay, and then again, you can turn this into 0. So here we have R3 plus 1 R2. Okay, and here we will obtain the following answers: 0, 1, 0. Here is 0 plus 0 is 0. Negative 1 plus 1, 0. 0 plus 0, 0. Here is 0 altogether. So based on that, we can clearly see that C2 is equal to 0. C1 is also equal to 0. Okay, and therefore, since this is actually trivial solution, okay, therefore we can say that B, which is a set of vector 1 and vector 2, is linearly independent. Okay, and since the condition 1 and 2 are fulfilled, okay, so here is condition 2, here is condition 1. Therefore, B is our set, consists of vector 1 and vector 2 here, is said to be the basis of W1. So this is the vector space. Okay. Right, let's move on to the next example here, which is asks you to find the basis for this vector space. So here is the vector space, and you can see that it is defined as polynomial of degree 3. So here is polynomial of degree 3. Therefore, you can think of example of vectors that fit the idea of this polynomial given here. Okay, so for example, you need to think, or you need to construct an example of polynomial of degree 3. For example, you can call it ux is a polynomial of degree 3 that fits this kind of description. That means if you have the value of a as a constant, this value of a appears as the coefficient right next to x cubed. So for example, if a is 1 and b is 0, so 0 has to appear right here and right there. So we can have a polynomial function that looks like this: 1 plus 0x minus 0x squared plus 1 times x cubed, which can be reduced to 1 plus x cubed. So this is an example of a polynomial degree 3 that fits the description given, or the description defined for that particular vector space. So again, choose values of a and b that are easy to come up with or to calculate. Okay, so that is an example. So we can choose another vector. Okay, so maybe we can call it vx. So what happens if we let a becomes 0? So a is 0. So here we have 0 plus 1 times x minus, so b is 1, so here is b, which is 1, x squared plus 0x cubed, which can be reduced to x minus x squared. So this is an example of another polynomial function that fits this kind of description given here. So I can think of this as set B. So B here consists of ux and vx, and I'm going to try and demonstrate that B here is the basis of this vector space. Okay, so the first thing that we need to do is we need to show that B spans W2, is it? So we need to be able to show that, and by doing that we need to perhaps think of the possible linear combination between these two items here. And of course, if you look at it, this ux here can be written in a slightly different notation, notation that incorporates this idea, where you have the position of constant, the position of x, x squared, and x cubed. So when you have 1 plus x cubed, this is the same thing as having 1, x is 0, x squared is 0, x cubed is 1. So that is the same thing as this one, but we use a different representative or different notation, that's all. Okay, so the same thing can be said for vx. Well, we don't have constant here, so constant is 0, x is 1, x squared is -1, and x cubed, there's no x cubed, so 0. Therefore, our objective, in order to show that B spans the vector space here, what we need to do is we need to think of the combination of these two vectors here, which is 1, 0, 0, 1 plus C2 and this is 0, 1, negative 1, 0. This should be equal to something, and we can represent it with alphabets. So what kind of alphabets that you want to represent? You can of course use X, Y, and so on, but here you can see when you talk about this vector space here, you can represent it in terms of, well, this is a constant, this is A, this is for X, B, this is for X squared, negative B, and this is A. So then you can represent it as such. So it should be A, B, negative B, A. And I hope that you can see the problem that we have right now. So at this point of time here, we have got the same problem as what you have seen in here. It has the same starting point, and of course if you keep on doing it or following the same procedure which I have outlined in the previous example, you will be able to show that B spans W2, and then you will go on and you should be able to show that B is linearly independent, because like I said just now, we have exactly reduced this problem here. So this problem looks different, but at the end of the day, when we do all this process here, we get to the point where we have the similar starting point as to the problem that we have discussed in this part for question 1. Okay, so the process here will be similar, so you just have to go through all the process here again. Okay, and you will be able to show that for example, this set here is a basis for this vector space that is defined as polynomial of degree 3. Okay, so go on and try and do that. I'm just going to move on to the next example here. So in this example here, we have a vector space that is defined in terms of a 2 by 2 matrix. And here there is a specific arrangement where you have to have the same values for these two parts, and the values here is also the same but different in terms of negative and positive sign. So therefore we can think of example of matrix as such. So again, we choose easy values to calculate. Okay, so for example, we can choose A equals to 1, B is 0, so therefore negative B must be negative 0. We must make sure the values here are the same. They are just different in terms of negative and positive sign. And here A is equal to 1, therefore this part here has to be equal to 1. So that is U, an example of a 2 by 2 matrix that follows the definition given here. And in order to demonstrate all the conditions necessary for it to be a basis, we need at least 2 vectors. So for example, we can come up with vector V. So vector V here could be something easy to calculate as well. So we can let A becomes 0, B is 1. So therefore here is negative 1 and 0. Okay, and I'm going to call it as B, a set which contains U and V, matrix U and matrix V. Okay, and for it to be a basis, we need to show that the first condition is fulfilled. The condition here is, does B span W3? So in other words, we need to show that there are values of C1 for the combination of this matrix plus C2 0 1 negative 1 0, where the result here is going to be something, and we're just going to call that as A, B, negative B, and A. Okay, so based on the matrix here, I'm sure we can create some sort of equation. So for those that want to see how the equations can be created, it will be like for example, for this one here, if you multiply 1 times C1 plus 0 times C2, the answer you get is A. So that is the first equation that we can obtain from the representation of these matrices, okay? Next, if you consider C1 times 0, so 0 times C1 plus 1 times with C2, the answer is going to be equal to B. Okay, next, C1 times 0, so 0 C1 plus negative 1 C2, the answer is going to be negative B. And then for this one is 1 times C1 plus 0 times C2, the answer is going to be equals to A. Now, based on these linear equations clearly, so this is the system of linear equations, we can construct the usual augmented matrix. Okay, so the matrix will look like this, where I'm just going to use the space right next to it. So from here, so if you study this first equation, it will look like this. So 1, 0, and A. For the part here, 0, 1, and B. So notice we have C1 at one part and C2 on the other part, yeah? And then here we have 0, negative 1, negative B. And here we have 1, 0, A. Now, I'm sure that you can see what we've got here is similar to the starting point of this example, the first example that we've discussed. So it's similar to this. Okay, so if you do the ERO, if you do all the elementary row operations, you will come to the same conclusion. So let's say you do the elementary row operations, and you will end up having the results looking like this: 1, 0, A, 0, 1, B, 0, 0, 0, 0, 0, 0. And therefore, you can clearly see that the value of C2 is B, the value of C1 is A. And following the same argument as in the first example, we can clearly demonstrate that B here spans W3. Okay, so that's the first one. And sorry, I just skipped a few steps because what I'm trying to show you is that the examples given here look different. Okay, first, this one looks like you're dealing with matrix of 2 by 2, and the example here is like you're dealing with polynomial of degree 3, and the example given here is related to some real number with fourth dimension. But at the end of the day, you know, all the examples here, although they look different, but at the end of the day they converge to the same solution. Okay, so that's the point really. And you will see that if you follow the same procedure, the same complete procedure which I have talked about in example 1, you will see that for subset of B, where you have matrix U and V defined as such, you'll be able to show that the set here is a basis for this vector space. Okay, so I think I just leave the rest of it to you guys to do it on your own, and I hope this video has been helpful, and I'll see you in the next video. Okay, thank you very much for watching.